Okay, hey everybody. This is lecture 10. Sorry that I wasn't able to make it to class on Thursday. The lecture's on unstructured meshes. As you may have seen from the Piazza post, homework 6 will be on marching tetrahedrons, and the way that you get tetrahedrons in a mesh is through unstructured meshes. We talked about this topic at the beginning of the term, but I wanted to discuss it in more depth now so you felt confident about unstructured meshes going into the project. I want to acknowledge Brent Leslie. Brent gave this lecture 2 years ago when I taught the course. Brent was a PhD student that I advised who's now defended and is off in industry. And so he actually wrote some of these slides. So let's see. So here's an agenda for the lecture. I'm going to review structured meshes, which is what we've been dealing with so far, but just to give some context, and then talk about unstructured meshes and cell interpolation within unstructured meshes. So for structured meshes, we've seen certainly the stuff on the left so far. So we've been talking about rectilinear grids, and rectilinear grids mean that the distances between adjacent cells can vary. So it might be that, the distance between this little far left and the one next to it is 1 unit, and the distance between this one and the one next to it is 2 units or something. Now in this case, they're all the same distance. And so these aren't rectilinear, they're uniform. The distance between any neighboring cells are the same. And in 2D and in 3D. And we've been dealing with that all term so far. This is a curvilinear mesh, which we haven't talked about very much, or grid. VTK calls them grids. I tend to use the word mesh. In fact, I'm sure when I lectured, I talked about meshes. And so the idea behind a curvilinear mesh is you can put the vertices wherever you'd like, but there's some implied layout to the cells. And so here's a given cell, and it has a cell to the right and to the left and to the top and to the bottom. And every cell has neighbors to the top and bottom and left and right, and in 3D front and back, unless you're at the boundary, in which case you don't have a left neighbor. Now, this particular curvilinear grid is laid out so that the vertices are all in a very organized fashion, and it actually would probably be possible to auto-generate these vertex locations. But the idea behind a curvilinear mesh is that all these locations are explicitly arranged, and the only thing that's implicit is the where the cells go. With rectilinear and uniform, you need far fewer numbers to specify where the points are going to go. Okay, and so let's see. So I think I've already said these things, regular mesh, and so Brent put in an example of uniform spacing. I already said that it could have different spacing. Here it is in 3D, and then here's the curvilinear. And this is a three-dimensional curvilinear example. It's a little tough to see. This is kind of the center of an arch right here, and then this is as it extends into 3D. And so this is just a curvilinear mesh in 3D. So what I really want to talk about is unstructured meshes, and we showed this plot, this picture before, but I want to show it again. This is an unstructured mesh that has 3 cells, and so the 3 cells, 2 of them are hexahedrons, so we can see one hexahedron here and another hexahedron here, and the third cell is this pyramid right here. Now, it says cell equals shape. I don't like that. Let me change that right now. Cell equals element. And so this one has, and so then there's different types of elements, and I'll actually have more of them in following slides. And so this particular example has 3 cells, which, as we already said, and 13 vertices. And you can see them labeled 1, 2, 3, all the way up to 13. And so in VTK, here are the types that are supported. This is actually a little dated because they have more than 14 types supported. I think these are the right 14 to show. The way that they have more types is actually they have what are sometimes called higher order element types. And so you'll see stuff like this where instead of having a flat edge, it'll actually be a curved edge, and they put some sort of like curve in there. So it's extra points that act as attractors and make the edges curved, and the math gets a lot trickier. The reason people do that is because sometimes with not much data you can represent really complex things, and that's sometimes a really good thing, especially when you think about like the cache hierarchy. But we're going to focus on linear elements for the entire term. And so, what are the cell types? A vertex, a polyvertex. I've personally never used a polyvertex. A line. I can't imagine uses for polylines. Basically, if you have a whole bunch of line segments, you don't have to, if you implement them with lines, then every one of these lines you have to put in this endpoint and that endpoint. And if you do it here, you can specify all these line segments, but you only have to specify each vertex one time. So you get about a factor of 2 savings. With applied vertex, you don't really get any savings. Here's triangles, and we've been dealing with triangles because that's the outputs that we think about. And here's triangle strips, and it's the same sort of thing that you can specify 3 vertices, and then the next vertex connects to the last 2, and so on and so on. And when I was, just getting out of college and thinking about doing graphics program, this was a big deal because it led to about a factor of 3 savings on how much it took to save the meshes to represent them with triangle strips. And people would come up with algorithms to take a lot of triangles and put them in triangle strips to achieve that 3x savings. I don't think that's as big of a topic today as it was then. Polygons. Actually, I don't see this used a lot in VTK. Sometimes algorithms don't work very well in polygons because they have these weird concave things. Pixels, and so pixels are just quadrilaterals, except for they lie along the x and y axes, quadrilaterals. And then really the thing that's important for today's lecture, which is a tetrahedron, which in VTK they call it a tetra for short. And so the idea here, sometimes my brain has to look at these for a little while. What I'm seeing a triangle that's flat on a table for 0, 1, 2, and then I'm seeing the third point come out of the table and connecting to 0, 1, 2. And so again, here's the flat thing, and then here's the third point, and so we can only see the front 2 faces. This triangle that's dotted on the bottom would be flat on the table, and this triangle right here would be away from the viewer. And so we'll talk more about tetrahedrons when we talk about marching tetrahedrons. Here's voxels, and so voxels are like the 3D equivalent of pixels, where the edges all run along the x, y, or z axes. Hexahedrons are the voxels, except for the edges can go in arbitrary directions. By the way, in VTK, they have different conventions. I think this came up in class. Voxels 0, 1, 2, 3, 4, 5, 6, 7, and hexes are 0, 1, 2, 3 going like counterclockwise and 4, 5, 6, 7 counterclockwise. Also a wedge. So a wedge is like a pup tent and a pyramid. So in this previous example, I was saying it had 2 hexahedrons and 1 pyramid. Perhaps these are 2 voxels if they're all axis aligned. But also a voxel can be represented as a hexahedron. A hexahedron cannot be represented as a voxel, at least in general, because hexes allow for edges that aren't axis aligned. Here's just an example of an unstructured mesh. And so this has 93,000 cells, a mixture of tetrahedrons, hexahedrons, wedges, and prisms. And so these are the cell types we were just talking about. And you can see you can put data where there is data, and if you want to have regions where the simulation doesn't take place, then that's no problem. Okay, so did I get this wrong? I did. Okay, sorry about that. Okay, so here is the same picture and showing the locations of the 3 cells. And or of the 13 vertices, at least, I'm sorry. I'm not going to restart it. Here we go, starting over. This shows for cell 0 the location of its 8 vertices. And so it's got it says vertex 10 is at the origin, vertex 11 is at 1, 0, 0, vertex 8 is at 1, 1, 0, and I'll just do one more. Vertex 2 is at 1, 1, 1. And so the question I'm asking here is if we stored each cell like this, where if I wanted to hand you cell 0 and said, well, cell 0 is a hex, that's one piece of information. I hand you a cell, I have to tell you what type it is. It's a hex, it's a tet, it's a wedge, whatever. And then for each of the vertices, what are the locations? And so the question is, how many bytes would this take? And I actually haven't looked at the next slide, although I can see a little 268 right there. But let's see if I can get that. So first off, there are 8 vertices, and each vertex has 3 values. So that's 24 values, and each of the values takes 4 bytes. And so I guess that sounds like 192. And then there's an integer right there. Now I have 268, and so what I'm saying is that there are I think this one, the reason the answer is 268 is I did perfectly fine calculating that there was 24 for cell 0, but there's also 24 for cell 1 and then 15 for cell 2. And I think that I said 196, but I should have said 96 because 24 times 4 is 92. I saw this big number and somehow my brain was trying to get to a big number. So again, I'm not going to restart the video, but the explanation I was doing was only for cell 0, that this would be 3 times 8, 24 values for this one, and then 15 for that one. And then multiplying each of the floats by 4 is 268 bytes. And then it also looks like I have these 3 ints, which is saying the first cell is a hex, the second cell is a hex, the third cell is a pyramid, and then one more integer in there, which is how many cells are there total. And so, I apologize for not reviewing this slide more closely before starting my presentation, but this looks right to me, that I believe that I could write something to disk and say, oh, there's 3 cells, the first cell is a hex, and so that would mean that I'd need to give it 24 floats, and then here are the 24 floats, and then the next cell is also a hex, another 24 floats, and the last cell is a pyramid, and then 15 floats. Okay, now here's another way of doing it, and this is how it's typically done in practice. And so the idea is that we could specify all of the point locations ahead of time. And so here are our 13 point locations. And so point 1 is at x equals 0, y equals 1, z equals 1. So there's point 1 right there. And point 13 is at x equals 2.5, y equals 0.5, and z equals 0.5. So there's point 13 right there. And then for each cell, rather than specifying which, if I say it's a hex and then giving 24 values, we instead only give 8 values, and it's the offsets, the locations within this list of points. So, I could describe the first cell, the hexahedron, as it's made up of points 10, 11, 8, 7, 4, 5, 2, and 1. And then I would take that information and go to this list and find points 10, 11, 8, 7, 4, 5, 2, 1. And so the savings here is that if you have vertices that are shared between the 2 cells, we only have to store those vertices once, and then we can access them multiple times. So it says if we stored each cell like this, how many bytes would it take? So I'm getting hipper here in terms of what I'm looking for in this slide. We're going to need 4 bytes, 1 int to say how many points there are, and another int to say how many cells there are. And then here we're going to need to store 39 values for the 13 vertices times 3 and xyz for each. So this looks like for the points we need 1 to say how many points, and we need 39 floats, 1 int, and 39 floats. And then down here, it looks like we'll need 1 int to say how many cells there are, plus 3 ints to say what the type is. It's a hex, it's a pyramid. And then it looks like we're going to need another 8 plus 5 ints to store these indices into the point list. And so that looks like that's 21 ints. I'm not sure we really come out ahead in this example. This looks like 25 ints, 26 ints, 39 floats. And so if we go to the next slide, it looks like this is 260 bytes. So the last slide was 268 bytes. You say, well, this is not worth it because this is more complicated. This one here that I've said we should call, and I didn't emphasize this when I was narrating this, that we should call this the explicit scheme. Here this took 268 bytes, but it's simple. Here's a hex, here's its vertices. You don't need to know anything more. And here's this other scheme that I'm saying we should call the connectivity scheme, because this array says how the cells connect. And it takes 260 bytes. It's only saving 8 bytes. And it's more complicated because you have to go to this list, and then it's an offset into another list. So this example is too simple. And if we had many, many hexahedrons, we'd actually see like a factor of 8 savings on this array right here. Or actually, you can get a factor of 8 is too large because all the vertices have to be stored multiple times. I think in practice it's about 2.5x. And so but that savings enough. And so people actually almost always in practice use the connectivity scheme and not the explicit scheme. Okay, now that I've described all that, in homework 6, I'm doing the simple thing. And when I hand you a tetrahedron, it will just have the 4 vertex locations and the field value at those 4 vertex locations. So I want you to know this connectivity scheme exists, but I'm actually not forcing you to use it for project 6. Okay, a little bit about cell interpolation. And so again, here's a tet. And so the way I'm looking at it, P0, P1, P2 are all flat on a table, and P3 rises up in the air. And then this dotted line is the thing I can't see. I can see these 2 faces, the P0, P1, P3 face, and the P1, P2, P3 face, but I can't see P0, P2, P3 because it's on the other side of the tet, and I can't see P0, P1, P2 because it's flat on the table. P is supposed to be inside the tetrahedron, and the question I'm asking is, if I know the value at P0, so I know F of P0 for some field, temperature, pressure, density, and I know the value at P1 and P2 and P3, so I have F of P0, F of P1, F of P2, F of P3, and I know the location of P, I want to know what's the value at that. And of course, we've been doing this before with linear interpolation, but we started with linear interpolation and then bilinear interpolation and then trilinear interpolation, but it's not as clear how to do that for a tetrahedron. So here's the game plan for doing this evaluation on an unstructured mesh. And by the way, if you do the volume rendering, this may come into play. If you do the volume rendering project at the end of the term instead of a custom project. So the idea is 3 steps, and these steps are words that we don't really know what they mean yet, but I just want to emphasize there are 3 steps. The 3 steps are you set up a parametric coordinate system, and then once you have that new coordinate system, then you calculate coordinates with respect to the new coordinate system for P, and then once you have those parametric coordinates, then you can calculate f of P as the sum of some weights. So 3 steps. What do these things mean? Let's find out. So the first is setting up a parametric coordinate system, and the idea is that if we have some for our 4 vertices, P0, P1, P2, P3, we'll pick one to be kind of the reference point, and that's in this slide is P0, and then we can set up 3 vectors, which is the direction from P0 to the other 3 points. So the direction in R is P1 minus P0, direction S is P2 minus P0, and direction T is P3 minus P0. And so those are 3 different vectors, and you can think of it in a similar way to you think of the X, Y, and Z axes. Those are 3 directions. In this case, the 3 directions are not orthogonal, that the angle between them is not 90 degrees, but it turns out that they actually are linearly independent if you've taken linear algebra. Meaning, really in this case, I think linear independence is the right word. What I really mean is, if you take small steps in R, S, and T, or some combination of steps in R, S, and T, you can get anywhere inside this tetrahedron, and actually anywhere in space if you take many steps in any of the directions and include negative steps. So really, that's probably too much information. What I want to say is, we're setting up a new coordinate system, right? When we have a coordinate system, when we say 2, 3, that means 2 steps in the x direction and 3 steps in the y direction. And so this is a different coordinate system, and it's a coordinate system made up of R, S, and T, and that's fine. And so this is a new coordinate system that's specific to this tetrahedron. And so then the next step is that we want to figure out how many steps do we need to take along R, S, and T, and we'll call these steps, the steps in R as A, the step in B, steps in S, we'll say we want to take B steps in S and then C steps in T, Now, these aren't all like integer steps. It might be we take a half step in A, and a third of a step in B, and a quarter step in T. And if we did that, then it would be, I can't even reproduce what I just said, a half, a third, and a quarter for A, B, and C. Um, and then if we did that, it would get to P. Now, it turns out that if we want to find A, B, and C, it's easy to do. We can set up a 3x3 matrix using RS and T, which we know, and P0 in the place we want to get, and we can just invert the matrix and solve for A, B, and C. So I'm just going to remind you that we had a three-step plan. The first step was to set up a parametric coordinate system, which we did. It was RS and T. The second step was to calculate parametric coordinates, which we talked about here, which is we can just set up this formula here and then invert the matrix and get the values of A, B, and C. And then the third step is that once we know A, B, and C, then we can calculate the field value at P as being the sum of the field value for the other four vertices times some weight. And here are weights that are often used for a tetrahedron. So the weight along the weight that we'll use for P1 is just A, the number of steps in R. And if A was 1 and all the others were 0, then we'd get the value at, that would mean that P would be at P1 and it would get the value of P1. Similarly with P2 and S and P3 and T. And so again, at the end, the takeaway here is that if you can calculate ABC, then you can just take the sum of these weights and the field values, and you can get the field value at P. So I just wanted people to see something that was different than trilinear interpolation for how you can get a field value. And I know most of you have not purchased the VTK book, but they actually have really good descriptions of the weights and how to use this and how to do this whole parametric scheme. Thinking about particle advection, so that was an algorithm that we spent a lot of time thinking about. And so this was the game plan with particle advection. You start with a seed location. You evaluate the velocity, you displace the particle, and you keep doing that until you reach a termination criteria. That's a high-level description of particle advection. The step that changes here is evaluating the velocity. And there's two ways that this is different. One way that it's different is when I say I want to know the value at location x equals 0.5, y equals 2.2, it used to be quite easy to find that cell with a rectilinear grid. And now we'd have to work a lot more if we had, some unstructured mesh to figure out which cell contained that location. And then the other piece is once we now have the cell and we want to interpolate, we need to interpolate the velocity to the location within the cell, and then we'd be looking at one of these parametric schemes. But for the most part, particle advection is the same with unstructured meshes. It's just that we have to do this velocity evaluation differently. Okay, so the last thing I want to talk about is marching tetrahedrons. And so here's yet another tetrahedron rendering. Again, I envision V0, V1, and V2 is sitting on a table, and then V3 sticking out from the table. I can see the face 3, 0, 1. I can see the face 3, 1, 2. I cannot see the face 3, 0, 2 because it's on the other side of the tet, and I can't see 0, 1, 2 because it's flat on the table. And so the idea then with marching tets is, here's an example. If we want to take an ISO value of 0.5, and we know that f of v3 is 0 and f of v0 is 0, and v1 and v2 have values of 1, then we'll get a situation like this, where we know that we can look at the edges still, and we can say that the location of the ISO value should be between, it should touch along this edge, and we can calculate that. So, despite me telling you how to do parametric systems for interpolations, you actually won't need it for marching tetrahedrons, because you can do a solve where you can say, what is the field value at this vertex? What's the field value at that vertex? And are they on different sides of the ISO value? And if they are, you can use your formula to calculate some t, which is the distance you should go, and then you should go if t equals 0, you would stay at f3, at v3. If t is 1, you go all the way to v1, and if it's a half, you go halfway between them. If t is 0.25, you go a quarter of the way between them, and so on. And so for this particular example, I've tried to put these little maroon ovals at the 4 locations that correspond to being halfway between these, because we have an ISO value of 0.5 and the field values are either 0 or 1. And by the way, this is the hardest case right here to think about, and that's why I drew a picture for you all. And then you can envision if you had 4 vertices like that, you could do something like this, where it makes a quadrilateral, and then of course you have to make triangles, so you'd probably do something like this, where you would make a triangle that 2 triangles that look something like that. Now I've done the harder case. The easier cases are, well, if they're all 0, meaning they're all less than the ISO value, well, nothing. And if they're all 1, they're all bigger than the ISO value, then nothing. And then the only other case here is that you have 1 that's low and the rest are high. Let me just do that really quick. So now that's high, and then I would put that there, and I'm going to dispose of that, and you do something like that. And so then that's the other case where you have this situation where one vertex is low and the other are high, or vice versa. And that's not a super hard case to figure out. This is the one that typically requires drawing a picture. Now, one thing I haven't done is I haven't laid out any conventions for you. When you've seen me do this before, I say, here's conventions, here's the edges, here's the vertices, etc. And I think you guys have the tools that you can just figure all that stuff out now. So the prompt for Project 6 is actually quite sparse. See, I can put there, it says, note, this prompt is sparser than previous ones. I figure you were all getting the hang of this by now. It just says to do marching tetrahedrons. So there's some starter code, and the starter code loads data from a file. And then and I added a tetrahedron class. By the way, the tetrahedron class has a print statement. I encourage you all to be, stopping, implement just a little bit of code and test. There's a print statement in there. And the main function does all the loading and does some little VTK manipulation, which we'll start talking about in more depth this week. But then it calls this isosurface tet, and that's empty, and you'll need to implement isosurface tet to generate the appropriate isosurfaces for that tetrahedron, and you'll get a picture like this. And this is actually an image of a star exploding. I think if we go up to the top, it's actually this image right here. It's an isosurface. It's a little bit disappointing because this looks, I think, quite pretty, and this one looks less so. And the reason it looks less so is I had to coarsen it to make it small enough that it would be easy to download, because it's being treated as a tetrahedral mesh. If you do the volume rendering project for the final project, then you will operate on this same data set, but I'll actually hand you a very high resolution version of the data set so you can make a really pretty image like this one right here. So I think that's it. Project 6 is online and it's due on Saturday the 16th. I'm hoping that, if you came out of the IsoLines project feeling good, that you'll feel like this is a pretty straightforward project to do. That's it. If you have any questions, I guess you can go ahead and just post to Piazza, and I can answer them there. Thanks, everyone.